In this lesson, we're going to be graphing and solving quadratic inequalities. Our first example is very basic. We're just going to be graphing a parabola from y is less than negative x squared minus 4x. I already went ahead and graphed that parabola, and now we just want to figure out how we're going to shade this. I used a dash line because it's not inclusive. It's just less than. So um, that's why I got the dash line. And as far as what side of the parabola I'm going to shade, well, I'm going to be shading below the line, or the curve in this case, because the key to this is that y is in fact less than, okay? And since y is less than, which direction does y get less and less and smaller? It's this. Another way of viewing this is that any values of y have to be less than whatever the negative x squared minus 4x is. And negative x squared minus 4x equals this dashed line. That's what it creates. So we want y values less than that. So our shaded region will be right here underneath the parabola. Now, if it was greater than, we would shade above that whole region above the parabola. It's like everything but what I'm shading now if it was in the other direction. So this would be our solution for this one. We're also going to have to be able to graph systems of quadratic inequalities. The first inequality, the y is greater than x squared minus 3, is going to be my dashed line, because this is not inclusive, and I know that it's going to be opening up, whereas the other one's opening down. And we want all values of y greater than x squared minus 3. So anything above this curve would be the region we would shade in for this one. So I could shade in everything in here, like so. And the next one, we're going to be, I've made a solid line because it is inclusive. And this one, I'm going to be shading values of y that are less than the negative 2x squared plus 4x plus 2. So that's going to be below the curve. So this one will look like this. So we'll have the overlapping regions, like so. And our solutions to the system are going to be any points in the overlapping area. You substitute any of these points into both inequalities and they will be true. Whereas if you just had, substitute the ones in the yellow area, you would get solutions that work for the first one but not the second one. So I want you to kind of be aware of what that overlapping region means and what the single color shaded regions are. Now let's go ahead and solve an inequality by using a table. So this would be a different method. We only have an x value though. We do not have a y. So there's no need to have an x and y axis, and we're just going to use a table to help us. So the first thing I want to do is, since we're solving for x, we want to see, what this trinomial or quadratic really is. So we're going to have to subtract 8 on both sides from here and here. So that's going to leave us with x squared plus 2x minus 8 is greater than or equal to 0. So let's think about what that means. It's saying that we're looking for values of x here that will make this side larger than or equal to 0. I went ahead and I've filled out this table beforehand. The top one are the values of x, and down here this is going to be my values of x squared plus 2x minus 8, or when you substitute these values of x into here, this is the output of that. And so I'm looking for where are my solutions, where do they lie? And again, we're looking for values at which this is going to be greater than 0. So we're looking for positive numbers and 0. Well, I'll notice that we have 0 right here. This equals 0 here where we substitute -4 in, and it equals 0 here when x is equal to 2. Now, for values that are greater than or equal to, then we'll be looking at, oh, well, 7 is greater than 0, and 16 is greater than 0. So if I substitute in 3 for x or 4 for x, I will get values that are greater than 0. So my looks like on this side, my solutions include 2, 3, 4, and anything above that. And on this side, if I substitute -4, I get 0. And if I substitute -5, I get 7, which is a value greater than 0 as well. So -4, -5, -6, and values less than that are going to be solutions. So it seems like values greater than 2 and including 2, and values less than -4 and including 4 is what's going to be our solutions. And this is clearly going to be an or statement, since our arrows, if you will, or solutions are headed in opposite directions. So the way I'd write this is x is less than, and it also includes, so it's inclusive to -4, or x is greater than or equal to 2. So it includes an infinite number of solutions, but select solutions in this case, anything not between -4 and 2. So anything with these negative numbers is less than, so we don't include that. Okay, in our next example, we're going to try another way of solving for x, and we're going to be doing it by graphing. And the way that we do that is we're going to start off and we need to find what the x-intercepts are. And the reason for that is we're solving for x. The name of the game here is what does x equal? And normally, if it was just an equation, we would have an equal sign here, and we would factor or use the quadratic formula or one of the methods and find what x equals to, and that would be our two solutions, or one solution, or no solutions. But since we're dealing with a range, it's going to be a little bit different, but we're still going to start off the same. We need to figure out where our x-intercepts are. That's going to be our starting point. So I'm going to go ahead and use our quadratic formula, because that works for everything. So I'll start off with x equals -b, so -3, plus or minus the square root of b squared, so 3 squared minus 4 AC, so 4 times 1/2 times -2, all over 2a. So 2 times 1/2. So start working that out. -3 plus or minus square root of 9 and minus, and that's actually going to be plus, and let's see, it's going to be 2, 4, plus 4, all over 1. So x equals -3 plus or minus the square root of 13, well, over 1, but we don't need to have the 1 there. So we just need to figure out what these two values are. So x is approximately -6.61 and positive 0.61. And on our graph, that's going to include, that's going to be about, let's see, 1, 2, 3, 4, 5, 6, 7. So a little bit short of 7. And it's not going to include it. It's going to, I'm going to just put an open circle there. And on the right side, 0.61 is going to be real close to 1, but it's not going to include it because it's not inclusive. It's just less than 0, and that's going to be an open circle. So I know that this parabola is going to open up. I don't really need to know exactly what this parabola is going to be. It's going to go through these points. It's going to be roughly something like this. It would be a dashed line, and it's going to curve up like so. So roughly it's going to be something like that. Now what I'm interested in is the shading. So if I were to replace this 0 with a y, so if I were to rewrite this as 1/2 x squared plus 3x minus 2 is less than y, or in other words, y is greater than this, that would tell me that I'm going to have to shade above this curve. Since y is larger, it's opening up towards y. Excuse me. So it's going to look like that. So this is our solution region. But what I really want to focus in on is the x-axis, because again, we want to solve, for x. What is x equal to? And since this is our solution region, this little section of the x-axis is included in that solution region. So anything on this part of the x-axis is also a solution. So if we were to view this as a number line, okay, then we're going to be between -6.61 and 0.61. So everything between that. So that's going to be an and statement. So the way I would write my solution would be x is, so actually it's going to be an and statement, so it's going to be 6.61 is less than x, and x is less than 0.61. So anything between those would be a solution. So here's an example of this at work, an application dealing with robotics. The number T of teams that have participated in a robot building competition for high school students can be modeled by T of x equals 7.51 x squared minus 16.4 x plus 35. And we're only interested for values of x between 0 and 9 inclusive, where x is the number of years since 1992. So year 0 would include 1992 and then 9 years out from that. So for what years was the number of teams greater than 100? So when I'm setting up this problem, I'm looking, T of x is equal to the number of teams. So I'm going to say T of x, we want values of that to be greater than 100. T of x is equal to 7.51 x squared minus 16.4 x plus 35, and we want that value to be greater than 100. So I'm going to solve for this, maybe write 100 here, by setting it, well, not equal to 0, but greater than 0. So I'm going to subtract 100 on both sides, and that's going to give me 7.51 x squared minus 16.4 x minus 65 is greater than 0, and that's going to make it easy for us to determine what to look for on a graph. So we're looking for values greater than 0, which means values of x that will make y greater than 0. I've put this in the calculator, and I've adjusted my window so that my x min is -1, my x max is 10, and my y min is -80, and my y max is 80. And that gives me a pretty good graph. I don't really care about negative x values, and this shows me, you know, the curvature of the graph. But more importantly, I can see where the value of 0 is on here, and I'm looking for values that where the teams are going to be greater than 0 in our equation. So I want to figure out what that point is. So I'm going to go to second in calc, and I'm going to be using the 0 feature. So I'm going to go to the left of it and press enter, and I'm going to go to the right of it. Oops, a bit too far. Press enter, and it looks like about 4. I'm a little surprised. Usually it's like 4.1, but this is telling me 4. Your calculator might tell you something a little bit different. So any value for x that's greater than 4 will yield greater than 100 teams. So our solution, so it's going to be less than 4 years, I'm sorry, greater than 4 years, but we have that restriction where at 9, so it's going to be less than or equal to 9. So we would say, therefore, would be between 4 and 9 years since 1992. Okay, so our last example, we're going to be solving for x, but this time we're going to be doing it algebraically. So we can solve this quadratic formula. We can solve this by factoring, however you want. I'm going to go ahead and do factoring. So I'm going to pull out a 3, And that's going to give me x squared minus 3x minus 4 is less than 0. And my factors on this, so negative 4, that's going to give me a positive 1, so x plus 1 times x minus 4 is less than 0. So using the zero product property, my solutions are x is equal to negative 1 and positive 4. Now, this is not inclusive. I've set up a little number line here, and I'm going to plot these on here. And I'm going to use open circles. So this represents the x-axis. I'll open circle here at negative 1, and an open circle here at 4. Now I need to determine where all the rest of the solutions are, or actually where the solutions are, because negative 1 and 4 are not actually solutions. And the way I'm going to do that is I'm going to take a point from each one of these and test it to see if I get a true statement. So let's say I'm going to take negative 2, so I'm negative 2, and then in here I'm going to choose a value like something in between the 2 points, like 0, and then I want to get something to the right of them, maybe something like 5 or 10 or something like that. So let me start with negative 2, and I'll get 3 times negative 2 squared minus 9 times negative 2 minus 12 should be less than 0. And this is going to give me 3 times 4, that'll be 12, plus 18 minus 12 is less than 0, and 18 is less than 0, but that's not true. So this is not going to be part of the solution region. Now let me try 0. So I'll say 3 times 0 squared minus 9 times 0 minus 12 should be less than 0. And this is going to give me 0 minus 12, so negative 12 is less than 0. That works out. That's going to be part of my solution region between these two dots. And then if I choose one more on this side, let's take 10. I'll get, let's see, 3 times 10 squared minus 9 times 10 minus 12 should be less than 0. So this is going to give me 300 minus 90 minus 12 is less than 0. And let's see, that's going to give me 198 is less than 0. And well, that's not true. So my solution region is anything in between these two open points. So anything between these points will count as a solution, but not including negative 1 and 4 because they're not inclusive. So my solution in this case would be x, it was going to be an and statement, so it's going to be negative 1 is less than x, and x is less than 4. And this makes sense because if I were to think of, let's say, if I were to take a three-dimensional view of this, I'm sorry, a two-dimensional view of this, if I had a y-axis and an x-axis, my parabola is going to roughly look something like this. It's going to be opening up and it's going to do something like this. And if I were to place the 0 with a y, then it's going to be y is greater than, and I would shade anything above that. So anything between uh, or in the shaded area rather is going to be a solution, and so that's going to be an and statement, and it's going to be located between this point -1 and this point 4. So you can think of it like graphing that way as well, to see if you did that correctly. Anyway, that's graphing and solving quadratic inequalities.